So, first of all, welcome to the lecture of material science. Today, let's start to talk about solid solution. Before solid solution, I think let's have a quick recall about what we have learned on last week. Last week, we basically talked about the disinfection, including 4 types of the imperfection, especially defects. We have 0-dimensional defects, 1-dimensional line defects, and 2-dimensional area defects, and the 3-dimensional bulk defects. And we finished the topic of the 0-dimensional point defects, right? Including vacancy, self-interstitials, and interstitials, and substitutional. So today we are going to talk about 1-dimensional line defects. We call it dislocation. But there are some important points in the vacancies and the self-interstitial, and that's the we call the fraction of vacancy. So I want you to remember this equation very well, because this will be in your final exam. And please bring your calculator to calculate. Especially, we want to know the fraction of vacancy is related to the temperature. Okay, if temperature is high, the fraction of vacancy will be high. Okay, and also you know that fraction of the vacancy is related to the is something to do with activation energy, or we call bonding energy against thermal energy. So this will be the thermal energy, and this will be the bonding energy. And according to this equation, we will be able to find out the activation energy using this plot. Okay, as long as we find the slope, we will be able to know the activation energy. Okay, and there are some cases for you to understand the how to use this equation. We make an example of the copper, right? If copper reach the temperature at 0 Kelvin, there's almost no vacancies. But in fact, this is impossible, right? Okay, and when temperature go up to room temperature, we have some atoms missing in the copper bricks, for example. And once again we increase the temperature higher and higher, we will have more vacancies in the copper metal. That means we lose many atoms, or atoms run away from the copper metal, right? Okay, so these are the important things for you to know. And by the end of last week, we talked about solid solution. We know the solid solution, there are 2 types. The first one is called substitutional solid solutions. The second one is interstitial solid solution. And we skip this. We already don't know this. This is very easy. Okay, so this is substitutional solid solution means, or we call substitutional alloy, is we make example of copper and zinc. Because the size of copper and zinc are almost the same, very close. So you know that the copper will act the size of the zinc. So you replace zinc to from zinc to the copper. So this is a combination of copper atoms together. So this is what we call substitutional solid solution, substitutional alloy. That means the site of the zinc was replaced by copper atoms. Okay. However, there are another type of the alloy we call institutional alloy. Institutional alloy means that this is a iron atom, and we understand the carbon atom will be smaller than the iron atom. So the carbon will stay in the between the iron, not replace the side of iron. Okay, so this is called interstitial or alloy or interstitial solid solution. Okay, these two are very important, and this one will what we call it brass, right? When you play your instrument, you always use brass. You don't use copper or you don't use zinc metal. It's brass. Okay, and interstitial alloy, one of example is okay, carbon steel. Okay, this is to make iron harder, stronger. So we put a carbon into the iron metals. Okay, and now this solution tell you that you have a limit to put the solute into the solvent to become a solution. So the solute, the important thing is you have to dissolve the solute into the solvent. Okay, and there are four factors, and please remember these four because these four are very important for substitutional solid solution. Okay, the first one is called atomic size factor. The second one is crystal structure. The third one is electronegativity, and the fourth one are valencies. Okay, so let's take, and this is called Hume-Russell rules. Hume-Russell rule is especially for substitutional solid solution. And let's take a look at this one by one. The first one is atomic size factor. Atomic size factor tells us that in order to make solid solution, the type of the solution only when the differences in atomic radii between the two atoms type then about plus minus 15%. It's not 30, okay? You don't plus this 15 and minus 15 together. Okay, so that means that these two, the atomic radii is the differences between these two atoms. It will be about plus minus 15%. Okay, either this one bigger or either this one smaller. Otherwise, substitutional lattice distortion and new phase form. Okay, you will have new phase. New phase means that from FCC become BCC or something like this. So new phase form, we doesn't define this as a solid solution. Okay, so the first important point is atomic size factor. It has to be less than plus minus 15%. The second key point is that is crystal structure. For appreciable solid solubility, the crystal structures for metals of both atom types must be the same. That means copper, if you want to have a solid solution with copper, the fluorine atom, if you want to put a fluorine atom into the copper metal, and both type of the structure need to be the same. For example, it has to be if copper is FCC, you need to find out another metal which is FCC structure, so you can make solid solution. Okay. The more electropositive one element and the more electronegative one another, the greater is the likelihood that they will form an intermetallic compound instead of a substitutional solid solution. What does that mean? If you want to make a solid solution, the electronegativity for both atoms needs to be very close. Otherwise, it will form another compound called intermetallic compound. Intermetallic compound. In Chinese is 介金属. Okay, and a fixed composition. What's the definition of the intermetallic compound is a fixed composition, only fixed, not any proportion. Okay, a fixed composition. Okay, for the solid solution, it's not a fixed composition. Okay, so this is third point. The fourth point is valencies. If you find that these three are almost close, and then for the both atoms, the final option or final things you need to concern is valencies. Other factors being a metal will have more of a tendency to dissolve another metal of the higher than one of the low valency. That means what? That means according to electronegativity in the periodical table, if you want to have a good solid solution for both A and B, then for the solvent, for the solute, you need to find an element which has a high electron valencies, like +3, valency will be +3, +4, something like this. Okay. Right. So let me summarize key words for you here. The condition for the substitutional solid solution, this is called Hume-Rothery rule. The first one, the differences of the atomic radius will be less than 15%, that's 0.1. The second thing you need to consider is the same crystal structures for pure metals, FCC, FCC, BCC, BCC. Okay. Third point, approximately in the periodic table. That means what? That means you have the similar electronegativity. If you have a large difference in electronegativity, it will be easier to make intermetallic compound instead of the solid solution, alloy. Okay, the fourth point is valencies. The valency is all else being equal, a metal will have a greater tendency to dissolve a metal of a higher valencies than one of lower valency. Okay? Right, so this is one of example of substitutional solid solution copper and nickel. Okay, the copper and nickel is two elements are completely soluble in one another at all proportions. That means copper and nickel can be 50-50, can be 60-40, can be 30-70. It can be put in all proportions. And this is what we call solid solution. And especially copper and nickel, the size of the copper and nickel are very similar, are very close. So this is a substitutional solid solution. Okay, so why these two can make a perfect substitutional solid solution? That's because according to these four factors, and the size of the copper and nickel is very close, and the crystal structure is the same. Okay, electronegativity very close. Okay, and if you want to put nickel into a copper, you choose the higher valencies. It's very close. So, so according to these four factors, copper and nickel can make a perfect substitutional solid solution. Right. So, in your final exam, this type of the equation will show up in your final exam paper. I would say probably 100% will show up in your final exam paper. So please remember. Right, so the question one here is, would you predict more alumina or silver to dissolve in zinc? Which one? Alumina will have more alumina dissolve in the zinc or silver into the zinc? Which one? I will give you a table like this. You need to find out the correct answer. So which one? So zinc is here. Zinc is the atomic radius is about 0.1332, and the crystal structure is hexagonal closed pack, right? The electronegativity is 1.6, and valence is +2. So how about aluminum? Aluminum is 0.11, right? Silver is what? Silver is 1.445. They are very, very close, but aluminum is closer, right? Aluminum is closer. Okay, and then crystal structure. Crystal structure will be FCC, FCC. These two are not the same as HCP. Okay, so these two doesn't fit. And now let's take a look of the electronegativity. This is 1.9, this is 1.5. And according to the Hume rosary rule number 3, tell you that you need to have a higher electronegativity, right? Okay. So answer is what? Answer is these two cannot be in 3% substitutional solution, but in complete solubility. Okay. And how about zinc or aluminum in copper? Copper here, FCC. Zinc will be HCP. Aluminum will be FCC. Okay. So if you according to this, and you find out that aluminum will be is better to the compared to the zinc. Right. So you need more practice for this. So please check out one by one according to the Hume rosary rules from number 1 to number 4. Okay. Right. So the second type of the solid solution is called interstitial solid solution. Interstitial solid solution is that the size of atom is much smaller than the size of the atoms. So I should say solvent, right? Solvent, and this solute. So for the interstitial solid solution, something like this here, and then impurities atoms fill the voids or interstices among the host atoms. So instead of replace the original atom, the impurity atom or the interstitial atom will be between the atoms, right? So the atomic diameter of the interstitial impurity need to be less than that of the host atoms, much less. So the typically is about 45% smaller than the host. So for the substitutional is about within the 15%. But for the interstitial solid solution, that will be less than 45% or smaller. Okay. So the metallic materials that have the relatively high atomic packing factor, that the interstitial position are relatively small. So what does this mean? If you have a FCC structure, that means atomic is 0.74. That means 74% of the space was occupied by atoms. That means you have less space to put interstitial atoms into this structure, right? So that means what? The interstitial positions are relatively small. So what's the biggest in terms of the metal structure? Simple cubic, right? Simple cubic. Simple cubic has only 52% of the space occupied by atoms. So you have more space to put interstitial atoms, like carbon. Okay. So, however, even though you have 50% empty space in your structure, but you cannot fill up 50% of the space in the crystal structure. Instead, the maximum concentration of the interstitial impurity is less than 10%. Again, I just want to tell you that although you have about 50% empty space in your crystal structure, but you cannot put a lot of atoms into this structure. The maximum is less than 10% of the space you can fill up with the interstitial atoms. So this is the example of the interstitial solid solution. We call it. We put a carbon into the iron. I hope you still remember, because the size of a carbon is much smaller than the size of the iron, and it need to be much less, like less than 45%. So the size of carbon is 0.071 nanometer. Iron is 0.012 nanometer. So it's still very different. The maximum concentration of carbon is about 2% into the iron. Okay. And why we need to put carbon into the iron? The carbon is the most common alloying materials for iron. Various another alloys elements are used, such as magnesium, chromium, vanadium, and tungsten. So this kind of metal, we all put the carbon into these metals. Why? Because it's called hardening agent. Hardening agent. Hardening agent tell you that, for example, you make this material harder, stronger. So carbon and another elements act as a hardening agent, the dislocations in the iron's atoms crystal lattice from the sliding past one another can be hardening for carbon, because you have atoms between the metals. So once you want to do the sliding means that you want to move, you want to pull from opposite side, and then this metal will be slide. Okay, but if you have atom between these elements, that will be metals, that will be difficult for you to move. So that's why we call hardening agent. Right, so I just want to have a quick summary for you. This is called substitutional solid solution. This is called interstitial solid solution, right? An example is copper in nickel or nickel in copper for substitutional solid solution. And this is called interstitial solid solution. For example is the carbon in iron metals. An important thing is that the atoms the impurity atoms are randomly distributed in the host atoms. Okay, this is carbon is randomly distributed, random distribution of the point defects. So atoms are randomly distributed in this body. Okay. Right. So this is another example showing you that B is B type atom, A is A type atom. Represent this. This is B. This is A. So as you can see, in this part, the B usually for a large amount of B, you put a lot of B into the A atom or A metal, and this area, or we call solid solution, because B is randomly distributed in this space. Okay, and called second phase particle, because as you can see, B and A pack very well in order, and this means that this is a new phase, And once we found out that B in A form a new phase, this is what we call intermetallic compound. So this second phase particle is intermetallic compound. Okay, so you have different compared to this place, and often different structure. Okay, as you can see, the concentration of B in this region is higher than here, right? Okay. Right. So let me summarize this. The zero-dimensional solid solution, zero-dimensional defect is substitutional. This is called substitutional, right? Substitutional impurity, and this is called vacancy. Okay, and this is called self-interstitial impurity. And we are going to talk about line defects here. But before that, we're going to talk about this next on Wednesday. We summarize this. Okay. Right. So for the section 4.4 is specification of the composition. So important thing is you want to define the composition. For example, that how many coppers atoms in this zinc metal, and you need to define the composition or the concentration, and how many atoms of the carbon in these iron metals. So there are two types. Easy. The composition, or we call concentration of the alloy in terms of its constituent elements. So there are two types common ways to specify composition. The first is the weight percent. So you calculate the weight percent of the copper in the zinc, or you calculate the atomic percentage. Atomic percent is what? Numbers of the atom of the copper in the zinc. Okay, atomic atom percent sometimes is more percent. You can use more, right? So I think this is very easy. I just want to skip this. So you know the concentration is M1 divided by M1 plus M2. The weight of M1 and divided by weight of M1 plus M2. Okay. And so atom percent is the mole, right? Mole of the M1. I'm sorry, this is 1. It's not M1. N1, okay? The numbers of the divided by numbers of copper plus the number of the zinc. Okay, and then, you know, once you want to, you know, the mole will be the mass divided by atomic number, atomic weight. So this is what we call conversion factor, right? The next topic is composition conversion. Composition conversion means what? How do you convert weight percent to the atom percent? Easy. Because the weight percent convert to atom percent is conversion factor is what? Atomic weight. I hope you still remember we talk about this conversional factor. We talk about this in when you are in first year. And another composition conversion is total volume. So this is mass per total volume. What that means what? It's kind of the dimension of density, right? Dimension of density. But here is not exactly the real dimension of density, because what you calculate is only the numbers of the mass of the solute divided by total volume. Okay. So how do you convert this? I want to skip this because this is very easy, and I hope this won't bother you a lot. So please read this by yourself. And if I want to have this, if I want to have this question in your final exam, I will definitely show you the equation. But I don't think I will give you this kind of easy question in your final exam. Okay, so please read this by yourself. And also you need to do the conversion of the atom percentage to the weight percentage or the mass total volume, something like this. Okay, so I don't have time, so I just skip this. So please do. So the summary is that of the alloy composition, you can use weight percent or atomic atom percent or mass per total. And you want to find out the alloy density, you can do it by weight, right? Mass per total volume. Okay, and important thing is how to find out the average of the alloy or weight and the conversion of these three. Okay, right. So finish the zero-dimensional defect. So now let's move to the miscellaneous imperfection. Miscellaneous imperfections. First of all, let's talk about one-dimensional defects. We call dislocation, or we call linear defect. The second one is the two-dimensional defect. It's called interfacial defects. The third one is bulk or volume defects, which is three-dimensional defects. And then the final topic will be atomic vibration, which is related to the temperature. Okay, so let's talk about dislocation in section 4.5. Dislocation also called linear defects. So what is linear defects? Oh, we call line defects, which is dislocation. So dislocation are line defects. And normally dislocation occurred when the slip between crystal planes resolve when the dislocation moves. This goes slip steps. So once you have a zinc and you pull this zinc bar from the top and from the bottom in opposite way, and you will elongate the zinc, right? And this produce a permanent deformation. So this is before deformation and after a tensile elongation. You pull up from the top and to the bottom. And once you use microscope to observe this part, and this part is a kind of slip steps. We are going to show you this soon. So this is called dislocation, or we call line defect. So what is dislocation? Dislocation is a linear or one-dimensional defects around which some of the atoms are misaligned to one line, right? And here we introduce three types. The first one is called edge dislocation. Second one is called screw dislocation. The third one is mixed dislocation. So first one, edge dislocation. What does that mean, edge? It's a dislocation line here, and this one will move to the edge. If we give some force for this. So this is what we call edge dislocation. Edge, from edge here to edge here. Okay, so let's think of a dislocation in principle, which is a slip or plasticity. So if we have atoms like packing like this. So we have atom, and this stream behave like a bonding energy or bonds between two atoms. So you have three-dimensional atoms packing like this in order. And if you use force from this side to this side, and that's what we call shear stress, right? Shear stress. And that means what? If you want to move this from right to the left, and move this line from left to the right. So how many force required theoretically according to the calculation? So this is called yield strength, yield strength. So yield strength, that means in theoretically, the yield strength will be a pair of the bond strengths. A pair of the bond strengths. This is the pair of bond strengths, right? One pair, one pair. And how many pairs you want to move around? You want to move 2, 3, 4, 5, 6, 7. So this is a pair of the strengths, and you need to times 7 according to this case. This is called bond density. So you need to times strength times 7. And this is called the theoretical yield stress. But when we do the experiment, we found something strange. When we do the experiment, we think that the measurement tells us that we don't need so much power to move this from left to the right. We only need about 1 out of 10, about 0.10% of the yield strength, and we can move this. And people think, why? Why? Because this theoretically bond strength need to times all the bond density. And why? What we need is only 10% of the yield stress. Why? So in 1934, Orlowen, he is a great scientist, an engineer. Actually, he is an engineer, and he realized, and advisor realized that the plastic deformation could be explained in terms of the theory of relation. So the theoretical yield stress doesn't work, but they found out that you can use a kind of theory, or we call this a theory of dislocation, to get this, and we only get 10% of the yield stress of the theoretical yield stress. And this is what we call slip. And this is what we can explain the edge dislocation. So assume when you have a carpet, you put it in this way, and you want to move this carpet to this location or to this position. So away. So what you can do, if you pull from the front, all the fraction will make you feel very to the right position, right? Okay, so in the case of a worker, they don't do it in this way. They use, in Taiwanese, luki. Understand? Okay, they don't use by force. They just move it one by one. You know, it's like this worm. He want to move. This worm won't put all his 10 legs and move around. He will luki, you know. He will move like this. I'm sorry, I don't know how to or English. Okay, so, and this save energy and save time, right? So this is the theory of dislocation. Okay. So the same thing happened in this way, is that this is dislocation line here, and if you move it one by one, you don't want to move it in all direction. I hope you still remember Coulomb. Newton Coulomb is represent electron, right? Electricity move like this. Electron doesn't move to the bottom, but electron move to one position and push out another electron away. That's why electron move so fast. So dislocation is that this is called the edge dislocation. This move to the end. So this formed by registration of the atoms. Okay, so because this is permanently deformed, so we call it plastic deformation or plastic shear. Or Okay, so as you can see, this is A, B, C, D, E into the N. Okay, easy. So if the dislocation doesn't move, the deformation doesn't occur. So if you want to deform this change of this material, you need to make dislocation line or dislocation plan, dislocation defects move. Okay, these are the explanation of the formation of edge dislocation. So dislocation can move if the atoms from one surrounding planes break their bonds and rebound. You know, the break bond and rebound. Okay, with the atoms at the terminating edge. In fact, a half plane of these atoms is moved in response to the shear stress by breaking and reforming a line of bonds. Only one line, okay? One or a few at a time. So the energy required to break a single bond is far less than that required to break all the bonds. That's why it's 10% of the shear stress, right? On the entire plane of the atoms at once. So this is three-dimensional edge dislocation. So edge dislocation where the extra half plane, this is half plane, right, of the atoms is introduced through the crystal, destroying nearby the plane of atom. Okay, this is the half plane. Okay. So let's have this is called edge line here, edge dislocation line. So we have a symbol like this. The edge dislocation line is perpendicular to this plane, to this slide. So dislocation use the symbol like this, a linear defects that centers around the line that is defined along the extra half planes of the atoms. So this is perpendicular to the plane of this page. This plane, right? Perpendicular to this page. Okay, perpendicular to this page. How about another symbol called Berger's vector? This is the dislocation line, right? And this is called Berger vector because this move one by one. And this vector is the Berger vector represent the direction and also the amount of the movement, right? So the Berger vector represents the magnitude and the direction of the lattice distortion of the dislocation in crystal lattice. So dislocation vector here and direction of Berger vector. Right, so distortion is within the regions around the dislocation line. There are some localized the lattice distortion because the shape is changed because of this dislocation line compared to this. So distortion means that you have an extra half plane here, and this part, and the shape destroyed or distorted. So distortion is the atoms above dislocation line squeezed together. The density here is higher because this is closer, right? So atoms between dislocation line apart below this because this was pulled apart. Okay. And the magnitude of this distortion decreases is the distance away from the dislocation line. So away, if this dislocation line from here, the distortion magnitude of distortion decreases. Okay. Right. So dislocations allow the atoms glide. There are two types. This type is called glide. From this side, it's called glide. If you move from this side, you move from this side, it's called glide. If you move from this side, it's called climb. Climb. Okay, just for your information, this is easy. Right, so this cartoon show you that this dislocation glide, right? From left to the right. From here, I move one step, move one step, and until you move to the end. And this is plastic deformation, right? Plastic deformation. And the climb, climb. Move upward, move downward. Okay, so this show you that, this we call that where is the dislocation half plane. This one, right? This one is dislocation half plane, because if you don't have extra this will pack together. This one will together. So this behave like this. And also your fingerprint here, this is dislocation line, something like this. Okay, so the second one is called screw dislocation. Why is screw dislocation? Screw dislocation means that you have a shear stress. For example, you move, take a look at this. If you have two planes, you like my hand, if you move one this side halfway and move one halfway this side, this is called screw dislocation. Okay, so let's take a look at this definition. The form by shear stress that is applied to produce the distortion is that the upper front region of the crystal is shift one atomic distance. This shift one atomic distance. Okay, on the top to the right relatively to the bottom portion. So you can move half, or you can move one. So this is called dislocation. So the example is this. Example is this one. The one on the top move this side, and the one in the bottom move to this side. So open circle is above, is on the top. The solid circles is in the bottom. Okay, atoms position below this one. So you can move something like this. And this place is called screw, because as you can see, this atom is in the bottom up, bottom up, bottom up. So it's like screw, right? It's like screw. So dislocation is linear and along the dislocation line A and B. So the line, and you behave like screwing. When you say you screw up, what does that mean? You screw up. You do something wrong and you cannot. You make a mistake, right? So the screw dislocation derive its name from the spiral or helical path or ramp. Spiral means what, right? It means this spiral or helical. So how about mixed dislocation? Mixed dislocation look like this. This is what? This is screw dislocation. As you can see here, this is dislocation, right? Line defects. So this is the mix of the mixed dislocation. So found in the crystalline materials are probably either pure H nor pure edge nor the pure schools, but inhibit components of the both types. It's called mixed dislocation. Mixed dislocation looks like this. This school dislocation, this edge dislocation. So this is three-dimensional, right? And if you take a look of the two-dimensional, and this is what we call mixed dislocation. This is school, and this is line. School dislocation and location. As you can see, this cartoon, this show you that school dislocation, this school dislocation here and line edge dislocation here. See that? School dislocation. Right, just show you here. Please take a look of this. We already mentioned Berger's vector, so I just just show you quickly this. Please read this by yourself. Right, so this is real. Is this a good example to show you that dislocation we can observe by TEM. TEM is transmission electron microscope. So this line actually, if you take a look of this, it will be easy. This is almost the microscale. Okay, so dislocation in electron micrographs. For example, this is titanium alloy, and you have line here, and this is called line. So, how are you going to form dislocation? I hope you still remember this picture, this image here. When you want to make gram or gram boundaries, you form from the liquid become solid. So all the crystalline materials contain some dislocations that were introduced during the series. The first one is we call solidification, from liquid to solid. So this is solidification. Okay, this is first one. The second one is plastic deformation. Plastic deformation means what? You use external extra force to pull the metal, and you make the metal deformed permanently. That's what we call plastic deformation. Okay, and also the consequences of the thermal stress that result from the rapid cooling. So you do the rapid cooling, you make the defects. It can be one-dimensional, zero-dimensional defect, one-dimensional defect, or two-dimensional defects. Okay, and this also applies to the same. This case also applies to the polymers and ceramics. Polymers and ceramics also we can find dislocation. Okay, so here are the examples for the dislocation and the materials classes. So for the metal, we understand like copper, like cobalt, iron, zinc, the dislocation. Why? Because you have atoms, and you have electron clouds. So it's like a glue, right? It's like glue. So once you want to change the shapes or want to deform, make a deformation. So and the bond is non-directional. Okay, so once you want to use force, it's easy for you to change. You want to deform. Once you want to make this dislocation, is easy. However, for the covalent ceramics, and the bonding, there's the bond between atoms, which is covalent bonds, and the bond is strong. So it's hard, it's difficult to move this, for example, like diamond, like silicon. And also, this bond has direction, so it will be easier for you to move to this direction rather than this direction. Okay. How about ionic? Ionic ceramic is like example of sodium chloride. Positive charge, this is negative charge. Again, the bonding is very strong, so it's difficult to move. However, once you move, negative go to negative, it will be repelled, right? So it's easy to break rather than deform. Okay. So these are the 3 examples here. And another example is dislocation mechanical properties, which want to know this is the structure, right? Structure dislocation related to the property slip, which is important. So dislocation move along the closed pack planes in the closed pack direction. So once we know which way is easier to move the one-dimensional defects, is it all the directions easy, or there are certain directions easier compared to another? So let's take a look. So pack planes have the most bonds. So this has the strongest bonding. So once you have strongest bonding, it's not easy to move, right? Because bond is strong and you have many bonds. So it's not easy to move in this plane. But between these planes, it will be easier, right? So, for example, we have a breast blanket 111. This is the plane FCC, and we want to know the planar density of this FCC 111. FCC 111 is what? It's represent to this the blue atoms here, So planar density numbers of the atoms center on the plane. This is the 111 plane, right? So we have 1, 2, 3, 4, 5, 6. You have 6 atoms, and per area of the plane. That's what we learn. Right? Okay. So this is the planar density, and if you look inside this will be the planar density will be this. This is 111. 111. And how many bonds here? This represents bonding. 1, 2, 3, 4, 5, 6. There are 6 bonds. So this is the most bonds, and that means that this plane has very strong. This plane is very strong. So strongest bonding is not easy to move. It's not easy to break, right? It's not easy to break the bonds. And what does that mean? So the 6 bonds planes, like B planes here, B balls, right? B atoms. And this FCC, this Cara blanket is 011. This is the hardest. The closed pack plane. This is closed pack plane for FCC. So once you want to move, move along the closed pack plane in the closed pack direction. So this is the closed pack plane, and can this closed pack plane move to any direction? For example, this direction, or this direction, or this direction, or this direction, or this direction. Which one is easier? The one is that the closed pack direction is easier way. So the linear density will be number of the atoms centered on the direction vectors per length of the direction vector, right? So if you need to find out closed pack direction. So the most closed pack direction is 0, 1, 1 in this way. You can move plane in this direction, or 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 this direction. These 6 directions are easier compared to move this plane in this direction or this direction. So always in a closed pack plane to use the closed pack direction in the closed pack planes. Okay. So this is the closed pack direction, and the direction where the atoms touch to each other, right? So that's the definition. I hope you still remember. PD stands for planar density. LD stands for linear density. And this is what we call slip systems. For mechanical engineering, this is very important. Slip system. Slip system is a set of the closed pack planes move back direction. This is the way you move the metals. When you want to move the metal, slip and need to be the closed pack plane and to the closed pack direction. For example, look at my hand. If I want to move these two planes, this can move like this all the way, right? But for a crystal, you need to move this is closed pack planes, but they only have few directions which is easier for you to move. For example, if it's easier for you to move in this direction, that means this is the closed pack direction, or this is closed pack direction. Now doesn't mean you can move it around like this. Okay. So slip system is that the dislocation does not move with the same degree of ease on all crystallographic planes of the atoms and in all crystallographic directions. No, it cannot. Only can move in a closed pack plane to the crystal plane to the closed pack direction. So the preferred planes which dislocation motion occurs is called slip plane. This is called slip plane. In the plane, the specific direction along which dislocation move occur is called slip direction. So this is slip direction. In two-dimensional, this is slip direction. The combination of the slip plane and the slip direction is termed the slip system. Okay, so slip system is the combination of slip plane and slip direction. Okay, so this is the example for you to understand. Here is that for the crystal structure, FCC, CN is what? Coordination number. Coordination, you have 12 coordination number, right? For example, this one has 12 neighbor, right? BCC have 8 neighbor atoms. SC has what? 6 neighbor atoms. So the highest density plane for FCC, we just told you, is 111. Right? Brass blanket, this is a family, right? You have how many? You have members of the family here. And then this is the higher density closed pack plane. And then you have closed pack direction. What is closed pack direction? I just told you. Okay, so this is 1 carat 011. How about BCC? BCC, the high plane is what? Which one is highest density plane? As you can see. Which one is 011? This plane. Or this one, right? This is the 011 family. And what's the direction? This direction, right? The closed back direction is this one. So what is this? 111. How about single cubic structure? It's 001. It's all the face planes. And then direction 001, the same. Right, so this is the systems, slip system, showing you that this is the closed pack plane, this is the closed pack direction. So when you take a look of the plastic deformation and by slips, And this is zinc, single crystal. If you pull the single crystal like this, you have a sleep, and you have sleep steps like this steps. And when you use microscope, you'll find something like this. So this is which is the close pack plan, and this way is close pack direction, right? Right. So let me. I think we run out of our time today. So on Friday we are going to talk about two-dimensional defects. Right. Okay. So that's it for today. I hope you enjoyed the lecture today.